So this is the lesson for the second assignment in the work standard, applications of quadratics number 2 here. So we have another very important applications of quadratics in free fall physics. So you definitely need to download this or print this somehow so that you can work with this. I'm going to do the first 4 problems and then 2 afterwards. And I'm going to tell you to focus on just doing a sketch of the graph, finding the x-intercepts, finding the vertex, and that almost always answers all the questions. The problem is, what are all the different graphs that can come up? So you have, they're all going to open upside down because of this negative 16, which is the acceleration due to gravity. And so some of them are going to start from the ground and come up and then down. Some of them are going to start from a height, come up, reach the maximum point, which is the vertex, and then come back down. And that's all based upon these 2 values. So the value multiplied by t is the initial velocity. So if it's positive, that means your object is traveling upwards to start with. And almost all of these, except for one, the initial velocity is positive. This is your initial height. And so this is the acceleration due to gravity that's acting on the object. So this particular object on this problem is going to start at 480 here. It's going to go up, reach a maximum height, and then come back down to the ground. And what you need to do is figure out what's the vertex point and what's this x-intercept. And that's going to answer almost always these questions that can be posed. So anything to do with the maximum height, that's a question about the vertex. And another thing you need to know is the independent variable is time, and height, in a vertical sense, is the dependent variable every time. So you don't need to write those in every time, but you should think about doing it. So this is the value here. So the B and C value tell you how to make your graph. Okay, time in seconds and the height in feet. So this is feet per second. And then this is 480 feet. So I'm not going to go through how to find the vertex. So you should know, actually I'll go through it once. You should know that it's done this way, and that you need to start your graph at that. So negative b over 2 times a. So this is 0.5. So the x value of the vertex is 0.5. And so when you do this, the thing to do, and actually now that I'm in here, I need to get the x-intercepts, which you get by using your app or the online calculator. So you got 2 different things to do. We need to get, so 6 and negative 5. So 6 is the one I want, right here. And then if we can made this over here, you know, this would be negative 5 on the left there. We're not interested in that one. So 0.5 is the x value of the vertex. And so you need to go in and graph this and start your table at 0.5. Oops. Start your table at 0.5, and then you will see that pattern. So that pattern, no matter what, has to show. So you see above and below the 484, how you have 468, 468, 420, 420. You do have the vertex. So 0.5, 484, you need to label that. This is actually 60 if you want, down there. And this is 0, 480. So that's all just, it represents time, height on the curve. So now let's use these to answer the questions. How long did it take for Jason to reach his maximum height? So half a second. What was the maximum height? 484 feet. Jason hit the water after how many seconds? 6 seconds. Now understand that's a high cliff. So yeah, some of these problems aren't, the values aren't really very realistic. Okay, problem 2. Notice 128 feet per second. I think this is in, yep, and 0 feet. So that means we're starting up from the ground, we're reaching a maximum height, then we're coming back down. And again, t is time, h of t is height. And you're going to find the vertex and the x-intercept in the same way that I've shown you. So you get the equation, which I've pre-done. They're in the problem here. You have to read the problem that's down here. So the vertex is 4, 256. The x-intercept over here is 8, 0. And this is 0, 0. And you need to interpret these points as after 0 seconds, I'm 0 feet in the air. After 4 seconds, I'm at a maximum height, 256 feet. And then after 8 seconds, so I reach it and I come back down due to gravity. And then after 8 seconds, I hit the ground. So it's good to fill all these things in. It helps to make sense in the problem. How long did it take for the rocket to return to the ground? 8 seconds. How long will it take for the rocket to reach its maximum height? 4 seconds. What was the maximum height? 256 feet. How many seconds will the rocket be 240 feet above the ground? There are 2 answers. So there's one on the way up and one on the way down. Well, you can get on your table and play some games. That's probably the best thing to do. You can set this equal to 240 and use your polysimult on it. Subtract the 240 over. I like using the table. I just think it's the best to make sense of things. Plus 128x. So we want to know, where is y equal to 240? Okay, so we can, let's just start at 4. That way we pick up the vertex. So, oh, it's on there. I thought we were going to have to do some finagling. 3 and 5. If it wasn't on there, you would have to use polysimult 2 to get it, or really do some finagling on your table. So after 3 seconds, it's 240 feet in the air, then after 5 seconds. So what I mean by using polysimult 2, you'd set it equal to 240, subtract the 240 over, and then just go in, and I'll do that real quick so you at least see it once. So you'd have negative 16, 128, and negative 240, because you have to subtract it over because it's equal to 240, the height. And then just hit solve, and then you'll get the 5 and the 3. So that's another way of doing that. Okay, 3 and 4. So step 1, write this up here. Step 2, look at your initial velocity. This is in feet per second, so we're traveling up. And look at your initial height. So we're starting at 101 feet, and we're traveling up. And then gravity acts on it and turns it back towards the ground. So again, we need to figure out these points using our apps. Okay, so the vertex is about 3.6, 311.3. Those are estimates. And about 8 seconds to hit the ground. So this is, again, estimates. So time and height. Three 3.6, 311.3. What you can actually do on your table when you do this, you can do the negative b over a right on your table So let me do that one time to show you. So when you put this in, 116x plus 101, when you go to your table set, you can do the negative b over a. So there's negative b, I'm sorry, over 2a. Right in the, so 2a is negative 32. It's always going to be negative 32 when you're dealing with gravity. You can just do that right in your table and it will like literally do it. So no matter what those values are, above and below it, you have to see that pattern. Okay, so I just rounded them off, then use polysimul to get the x-intercept. So again, you need to get all of these values first. So 311.3 feet, so that's the vertex. And then how long after it hits the ground? 8 seconds. It's really pretty easy to do once you get the quadratic figured out, but you have to figure it out before you do anything else. So notice here, 64, let's see here, feet per second. So we're traveling up to begin with, starting at 5 feet. So we're starting pretty low here and going up and coming back down. So 0, 5, and the vertex on number 4 is something 69. So let's actually put this in because I didn't do all the what's the maximum height of the grappling hook. We want to compare it to 50 feet. So you want to climb a ledge that is 50 feet above you. So here's this ledge that you're trying to throw it over. Draw that in there. And it's 50 feet. So we want to know, is the vertex point higher than that 50 feet? So I'm just going to put this in again and do this out. Plus 64x plus 5. So negative b, negative 64 over negative 32. That's going to be 2. So there's the vertex, 269. So it's going to get 69 feet in the air. We don't need to get the x-intercept here. You can, but so yes, 69 feet, yes, because 69 is greater than 50. It's going to make it over that height. Again, you can go in and figure out the vertex, or I'm sorry, the positive x-intercept there if you wish to. But it is not needed. Actually, I will do it just to be complete here. And the problems that I do, remember that you have to go to a root finder to find the x-intercepts. So 64 and 5. It looks like about 4.1. So about 4.1 seconds. Okay, let's move up to problem 9. So I'm going to do 9 and 14 and we'll call it good. So notice that on this problem we have no t variables. So that means initially our initial velocity is 0 feet per second and that we're starting at a height of 49 feet. So what that means is literally the object's being dropped. And the left side of the parabola would be over here. So that is the peak. The 049 is the vertex. And so just based on the way the description is. So if you have a situation like this with the initial velocity of 0, technically the object is being dropped from a height. So vertex 049, x-intercept about 1.75 seconds. So how long did it take for the anchor to reach the water? 1.75 seconds. And then what's the height when it hits the water? Kind of a goofy, 0 feet. So it's all about this question here on number 9. So you do have problems like that. So you've had 3 different kinds of graphs. One like this, one that starts on the y-intercept, and then one that starts on the ground. And you need to be aware of that as you do these. Now, I am going to show the other type of problem that can happen. Problem 14. So notice on this that we have a negative initial velocity. That's kind of weird, but is possible. And what that means is that the object is starting like you're throwing it down, and so like the vertex point is weirdly before, excuse me, and then the left half, so there's always like the left half of the parabola that sits over the negative region, but here it's has some speed to start with, traveling downward. So anytime that's negative, it's not very often it is, that means that the vertex point is actually in the negative piece of the graph, which is really weird, and so it's not even part of the picture. So about 6.50 is the x-intercept. Again, you're using all the apps that I've shown you, or online calculators and graphers, to get these values. Independent variable is height. Vertex is, we don't even need it because it's not going to be, you can get it, but it's going to be negative something and then with a height. So, feel free to calculate it, but it's not going to be part of this. So this is the 4th type. This is the only problem that is of this type with this kind of graph. So that's why I'm doing it. So how long does it take for it to hit the street below? 6.5 seconds. The vertex does not represent the maximum height of the rock. What then is the maximum height of the rock? 1,000 feet. So that's the only point, because it has downward speed on the positive time part of the graph, that is the highest point. So weird problem, but it exists. So let's just, for the sake of being complete, let's go in here and do this. So negative 50 plus 1,000. So we want to start at negative b, so that's going to be like 50 over negative 32. And you'll see, again, how above and below, right there, it's the same. It's goofy. So negative 1.6, 1039.1. Goofy, but can happen. Okay, so you have the rest to do for your second assignment. I do need to see the work, so make sure that you either use this or use a notebook piece of paper.